slide. You got it? Okay, I'll begin. Dearly Father, we thank you for this day. Again, Lord, I thank you for these students, for the weekend just completed. I just pray to be with us today. Help us to understand a little bit more about sequential limits and how to study them, Lord. In your name I pray. Amen. All right, so first things first, let me just, let's see, where should I start? So in section 11.4, there were a couple of remaining things that I haven't proved, and I said I'd put them off until we had L'Hopital's rule. So now we got L'Hopital's rule, right? So let's go ahead and just prove those. So first of all, ln of n over n going to 0. So what I do is I consider x going to infinity of ln of x over x. By L'Hopital's rule, this is type infinity over infinity, right? So I differentiate the top. Derivative of a natural log is 1 over x. Derivative of x is 1. I do algebra. This gives me the limit as x goes to infinity of 1 over x. Of course, this is 0, right? Therefore, well, then we make this argument. But f of x equals ln of x over x is continuous on 1 to infinity, and f of n equals ln of n over n for every natural number, right? So by the continuous extension theorem, which we proved the other day, the limit as n goes to infinity of ln of n over n is also equal to 0. I don't know about you, but this 2 sentences of writing is getting very tiresome to me. Would you like to know a shorter way of expressing the same sentiment?
Yes.
Yes, I think we would all like that. So here it is. And the reason I haven't said this up to this point is I didn't see it in the book per se, but it's something I regularly use, and it's a nice way of communicating the same level of precision, which is what we're interested in. We're interested in precise solutions. I guess one of the things I should start to emphasize to you guys is, maybe in your previous math class, you had a professor write stuff on the board, and they really only expected you to write some subset of that for the solution, right? And they gave you arguments, but they didn't really expect to hear all those arguments back from you again. That's not the case in here. I'm pretty much telling you what I want to hear back from you. Not that you have to memorize it, but I want you to understand the structure of the logic we're using and be able to write it back. And I want you to write it back in a similarly precise way to the way I'm writing things in here. I'm always trying to model the right kind of presentation of solutions in here. That's a continual goal of mine as I talk about anything. So I hope you're picking up on that, because as I graded the quizzes, there's some work to do. And I let go some stuff in the first test, right? I was just happy if you found an answer in some sense. And I kind of looked the other way with some wrong notation here and there. Right? I really can't do that with the sequence material. I have to insist that you write things precisely and correctly. So that's part of the reason we're having quizzes, to try to alert you to this reality so that you can try to, straighten your course. And because a lot of what I'm being picky about is easy to fix. I'm just saying you should write equals where there should be equals. If you're, it's fine not to write a limit, but you got to be careful with that too. Anyway, it's hard to communicate everything about that. That's why I'm always trying to communicate it implicitly with every example I do in here. Okay, so here. That said, here's a very nice shorthand for us. The limit as n goes to infinity of ln over n is equal to, by L'Hopital's rule, 1 over n over 1. And then I write over here, extending n to be a continuous variable, or you could say continuously extending n would be the same. The idea here is just that this n over here is a real variable, whereas that is just allowing n to take on discrete values, right, in the natural numbers. That's what the continuous extension theorem really says, is that you can extend a discrete variable to be a continuous variable in this natural way. So this saves me, right, all of this writing. But you got to be careful, right? If I try to extend n to be a continuous variable, and if the functions involved aren't continuous, oops, right? So we got to be careful with this language, understand what it implicitly demands of you. But anyway, they're 0. Any questions about this? All right. anyway, that's nice. Another example of this comes up in the proof of number 7 from section 11.4, which is a very important example. The limit as n goes to infinity of 1 plus x over n raised to the n-fold power is equal to e to the x. That's the claim. We want to show that. All right? So what happens here? Think about this. Well, as n goes to infinity, x is just some fixed real number, all right? So x over n is going to 0, whether x is positive, negative, or 0. It all goes to 0, x over n, right? So this is really 1 plus something going to 0. In other words, the base here is tending to 1. Of course, n tends to infinity, right? So this whole thing is what? It's type 1 to the infinity, right? Agree? So that's an indeterminate power. So we use our standard calculational trick. I rewrite it in terms of the exponential of a log. So this is the limit as n goes to infinity of exponential of the log of 1 plus x over n to the n power. Right? I can do that because I know that the expression I'm taking the limit of is positive, right? Certainly something that's close to 1 raised to some integer power is not going to be a negative quantity. So it makes sense to take the natural log of it. Then I use continuity of the exponential and the properties of the logarithm to pull the n down and to pull the limit inside, right? So, all right. And then I focus on the resultant limit here. I call it star because that's what I usually do. And so I have to focus on that separately. That's the limit as n goes to infinity of n times ln of 1 plus x over n. So look, the log is kind of sort of a function of 1 over n, right? X is fixed here. It's no n dependent. So if you can create the expressions, it's got like a 1 over n dependence upstairs and a 1 over n dependence downstairs. That's really nice because when you apply L'Hopital's rule, after we've extended n continuously, then we'll have the same minus 1 over n squared from the chain rule, top and bottom. And they'll cancel. That's so like it's in our best interest to take this, which is type what? Infinity times 0, right? By the way, this I don't expect you to write in your solution, just to be clear. That's like a bonus comment. That's not what I was just talking about. Okay. Limit as n goes to infinity, so I bring the 1 over n downstairs, right? Then I have limit as n goes to infinity natural log of 1 plus x over n divided by 1 over n. I do L'Hopital's rule after I have extended n to be a continuous variable, right? I can't do L'Hopital's rule on just pure sequential limits, logically speaking, because they're not a continuous variable. But I don't know, that's kind of a artificial comment because, of course, you could develop a whole theory of sequential limits, which is based on, like, taking the function, extending it continuously, proving the rule over there with the continuous function, and then transferring it back. Then you'd have a theory. You'd have a theorem in the theory in the sequential side. So the saying you can't do it on the sequential side is kind of artificial in my view. But it is something we say. All right, so after I extend n to be a continuous variable, I can apply L'Hopital's rule to type 0 over 0. I got to be careful, chain rule, right? So I get 1 over the argument of the log, and then derivative of that gives me minus x over n squared. Do you guys agree? Do you guys see where I'm getting the minus x over n squared? Here? Okay. And downstairs is simpler, right? Derivative of 1 over n is just minus 1 over n squared. But then they cancel, right? And the minuses cancel. And you're just left with x over 1 plus x over n. And that's not something we need any kind of highfalutin anything for. We can just use limit laws and evaluate it n going to basically allow n to go to infinity. Well, 1 over n goes to 0, right? So x over n goes to 0. And I've got x over 1 plus 0, but that's just x again. So go put it back up in here, and there you go. This is equal to e to the x. In other words, the limit as n goes to infinity of 1 plus x over n to the n full power is equal to e to the x. Yes, sir?
Might be rhetorical, but right there, the first one to the red, to the left. And how'd you get that 1 over n at the bottom?
Oh, that's just using algebra. So the algebra step here is that n is equal to 1 over n. Which is an important algebra trick for L'Hopital's. Yes, sir?
You say in this case x was a variable or a constant?
X is a fixed but arbitrary constant. I mean, this calculation goes through whether x is positive, negative, or 0. Although if x is equal to 0, it's easier. I don't really need L'Hopital. I mean, if x is equal to 0, I just got limit as n goes to infinity of 1 to the n. But 1 to the n is equal to 1 for any n, so that's just a constant sequence. So I hardly need L'Hopital's rule and fancy stuff if x is equal to 0. You should understand, L'Hopital's rules, I mean, if you go back and look at section 11.4, all right, and you look at the arguments he made in that section to get this conclusion, you'll see it doesn't look anything like this. I would say his arguments are more subtle, probably more difficult. This is just a direct calculation, right? Why is it easier for us? Well, it's very simple. L'Hopital's rule, as I told the earlier section, is a beast. And when you use L'Hopital's rule, you're entering beast mode. So you should use it accordingly. It is a non-trivial tool. But once you have it, this gives us an alternative way of looking at the exponential function. Some people actually take this as the definition of the exponential function. This formula naturally is derived from a study of compounding interests, where you take the number of compounding periods to infinity and correspondingly adjust the rate of the compounding to be smaller and smaller according to the number of divisions in which you're compounding. So there's a natural financial application which derives this formula. So I don't know. That's not it's not my personal favorite, but some people like this as a definition for the exponential, not me, but it's one of like 5 or 6 logically equivalent definitions for the exponential. All right. Anyway, that's it. Now I have nothing. I'm going to talk about the quiz the last 5 minutes of class, but other than that, the rest of the time is for your homework. So go for it. Do you want me to talk about these? This is number 35. It's got a sine here instead of a cosine. So I would say if you're faced with something like this, minus 1 over n to 1 over n, think about n going to infinity. What happens to both bounds? They're both going to 0, right? That's not especially important. If these were both going to 3, it wouldn't change it any. Like if I have 3 plus 1 over n and 3 minus 1 over n, both of the bounds going to 3, I'd have the integral from 3 to 3. What's the integral of any like continuous function at a point? I mean, it's by essentially definition 0. That's not a justification that the limit's 0, but that is intuition for why it should be 0, right? The justification, I can use this property of definite integrals, which is that, you know, if I'm integrating from a to b, some continuous function f, well, m times that and big M times that, where this is a minimum and a maximum. I know these exist by the extreme value theorem for what it's worth if f is continuous. So I have such a set of bounds. So I just basically apply this property of definite integrals to the function which is considered. So like, of course, minus 1 is less than cosine is less than 1 anywhere. It's certainly also true between minus 1 over n and 1 over n. So in this case, b minus a is 2n. So I get this. I get minus 2 over n is less than or equal to the sequence I'm interested in, is less than or equal to 2 over n, and then I just use squeeze theorem. And that gives me a justification for why it's 0. Intuition tells me at the start immediately that it's 0, though, because the bounds are equal in the limit. The only way that could end up being non-zero is if you had some sort of improper integral, but since we're at section 11.4 at the moment, that's impossible because that's in section 11.7. So it's not very interesting logic, but it's logic. This one, this problem 43, I assigned you guys 44. 43 and 44 are both just invitations for you to learn Gauss's formulas. Do you know what Gauss's formulas are? Well, he's got lots of them because he's Gauss. But this one he apparently knew as a child. So the teacher said, like, hey, add up the first numbers from 1 to 100 on your little slate board, and then, so he's trying to like burn some time for class, right? So as soon as he asks it, Gauss is just like 5,050. It's like, dude, what? You know, and so what he did was he's just like, it's 1/2 of 100 times 101, which is, by the way, 50 times 101, which is 5,050. I invite you to check that the sum of the numbers between 1 and 100 is in fact 5,050. But maybe you can try it for 10 instead. How about, I'll be even lazier. How about the sum from numbers of 1 to 5 is 1/2 of 5 times 6, which is what? 15. Check it out. Is that true? So this is in fact one of Gauss's formulas, that 1 plus 2 plus 3 plus da-da-da plus n is 1/2 n times n plus 1. This is the formula. Or you could write it more succinctly as this: sum I equals 1 to n of 1, of I, rather, in the summation notation. Well, there's a similar formula. The sum I equals 1 to n of I squared, aka 1 squared plus 2 squared plus da-da-da plus n squared, is n times n plus 1 times 2n plus 1 divided by 6. So, in that, where were we? I've had bad coffee timing lately. Like, the coffee is like at the very end of the first pot, and I just don't want to drink it because it's like, eh. But then it's nice to have coffee between class. I need to get some other professor to drink a cup of coffee a little bit earlier. Or I can just pour a cup out. That seems wasteful. I don't want to drink it, though. I don't know. I haven't solved this problem yet. I had better coffee timing earlier this semester. But this week, last week, it's not been optimal. So in, where was I? I'm talking about 11.6, I think. Can't remember where these problems were. Maybe, no. Where were these? 11.4? Yeah, 11.4, number 43, 44, and 45. Look, these are very silly problems. Basically, the point is you take this expression or that expression and replace it with Gauss's formula, and then do a rational sequence calculation. Like, for example, here's a toy example that's like 44. If I was to calculate this limit, 1 plus 2 plus 3 plus da-da-da plus n, since I quote-unquote know Gauss's formula, like, how would you know it? It's not profound. They gave you a hint, which means use the hint. So I can trade this for that, and then it's a rational sequence problem. So I divide by n squared, and I got a half for my problem. For your 44, the sum of the squares from 1 to n is like a cubic in n, right? It's like n cubed, but the denominator's n squared. What's going to happen there? If I have something third order in n over something second order in n, and I take the limit as n goes to infinity, what happens? It goes to infinity, right? It's going to be unbounded. But you should show your work, of course. All right, where were we? I think that's about it. Let me erase this stuff unless there's questions. You could prove these things by induction, but maybe I will someday, but not today. Yes, sir.
11.549.
11.5, number 49. By the way, despite my empty threats to prove L'Hopital's rule today, I will not make good on those. Maybe tomorrow. The Cauchy mean value theorem proof, I won't get to it today. I'm just saying. You guys are like, oh man, I'm very upset by that. I know. You'll get over it though. So, given that f is continuous, use L'Hopital's rule to determine. I'm not sure I can give a hint on this without just working on it. So you'll forgive me if I just work on it, yeah? Okay. I know you guys get very upset when I do your homework. Or stuff like your homework. All right. Actually, you should. Because the more of your homework I do for you, the less you learn. But there's some kind of balance between being totally stuck and getting nowhere and getting help. I'm not sure what exactly the right balance is. I usually err on the side of giving you guys help. We're supposed to use L'Hopital's rule to determine this, huh? Well, as x goes to 0, that integral is definitely 0, right? We're given that f is continuous near 0, right? And then x is going to 0. Well, this is, if I just rewrite this to emphasize what's going on, man, if I write much more, I'm going to have solved this problem. Right? So L'Hopital's rule says what? This is the limit. Well, L'Hopital's rule type 0 over 0 d dx of the integral un So can anybody tell me what the numerator is? Yes, sir?
Yeah,
F of x, why?
because the integral of A
Right. Right. This is fundamental theorem of calculus part 1, right? d dx of the integral from a to x, let's say, of f of t dt, assuming f is continuous at x is just equal to f of x again. So this is in fact just the limit as x goes to 0 of f of x. Yes, sir?
So when you use the integral with the limit, it does not mean that you have to integrate first.
Well, yeah, I don't think you could even do such a thing because you don't have a formula for f. I mean, you can't integrate it.
Let's say like the cosine x squared that you had already.
Right. Again, you can't do that integral. That's kind of the point of doing cosine of x squared is like this doesn't have an elementary antiderivative. You can't find a function whose derivative is that function in terms of elementary products or quotients of sine, cosine, exponentials, algebraic functions, transcendental functions, you pick it. I mean, an antiderivative exists because it's a continuous function, but not in terms of elementary functions which we know. So I can't. That was kind of that's why the homework problem is sine of x squared. There is to prevent you from actually integrating. Now, if you were to do this, just for fun, suppose you had something that was integrable, right? And the easiest thing to do would just say, suppose it's the derivative of another function. Then that function would be the antiderivative, right? Then this would have been f of 1 over n minus f of minus 1 over n by the fundamental theorem of calculus part 2. And then you could have argued that you got 0 because as n goes to infinity, this goes to f of 0. That also goes to f of 0. F being differentiable, it's certainly continuous. Hence the composite limit theorem applies, and we get f of 0 minus f of 0, which is 0.
It was pretty painful, but I got
But you couldn't integrate cosine of x squared. If you have integrated cosine of x squared, and I said this to the earlier section too. I'm sorry, but you're wrong. You no can do. You have deceived yourself somewhere in there. I'm not sure where, but well, take the thing you think is the integral of cosine of x squared and differentiate it. You'll see that it doesn't get you back to cosine of x squared. That's the fastest way I can convince you. But I guess in principle you can suppose, well, this is continuous, therefore some little function f exists such that df dt is equal to cosine of x squared. And then this should be df dx, sorry. And then you could run through this argument for an arbitrary f which you don't know the formula for. That's another way you could do that problem. I digress. Other questions that... Stop chasing this rabbit. Other questions, preferably about L'Hopital's rule. But I'll take questions about earlier sections if you got them. Yes, sir.
It's kind of like a technical question.
Sure.
When we do the L'Hopital, the symbol, the L to the equal sign, do we have to say what if it is in parentheses?
Yes, I would like to see, as I've always been writing, 0 over 0 or infinity over infinity. Yeah, that is a good question, an example of what I mean by I'm trying to write things as I'd like you to write them. Now, you don't have to write that. Another way you could have expressed yourself here, of course, is by L'Hopital's rule on type, 0 over 0. And that's what you'll see in textbooks a lot of time. Something, but it has to be indicated somewhere, yep.
Do you want us to use that exact notation for L'Hopital's rule? Because I've learned a different notation that I'm used to using.
Which is?
It's just an equal sign with an h over it. And so even if as I'm following on with your work, I find myself writing a different notation.
Oh, that's fine with me. Yeah. But just make a note for me when you... now that you've told me, I'll probably remember. But generically speaking, if you use some notation that I don't use, you should say at the start. Now, there are some things I refuse to accept. Like, I will not accept that if you've got x squared times f of x, that you're going to write that that's equal to x squared times f of x. I can't do it. I'm sorry. I cannot allow this notation. I will not allow it. Also, if you want to start telling me that 15 thirds is equal to 14 thirds is equal to 4 and 2 thirds, I can't do it. I'm sorry. I know you might have been taught it as a child, but whoever taught you that is wrong. And I don't care if hundreds of years of tradition establish this as being something you write. It's just not right, because if you do it, we multiply by 3, and we get 14 is equal to 4, 2, which is 8. And that's problematic to me. It's not cool, right? Because now if you wanted to tell me 14 thirds is equal to 4 plus 2 thirds, you know what? I'm right there with you. Cool. I got that. I'll buy that. But the other one, there are just a few things I can't let slide. You should be happy. I'm telling you, you don't have to reduce fractions, right? Some of you, like slaves to your mathematical past, still do. I don't know why. For yourself. Oh, okay. So someone has a question, yes? You guys must have questions. Yes? Hey, I like this problem. Sorry, Jordan. It's this one again. This is a rerun from earlier section. Number 10 is x times the sine of pi over x. I can't write. All right. So what type is this as you're thinking about it? That's the first thing I ask myself with any limit. It's like, what type is it? Can I just plug the number in? You know? Right. This is infinity times 0 because pi over x goes to 0, right? Sine of 0 is 0. So this is, yes, infinity times 0. So what I do is pretty much the same trick that we did in the exponential argument over there, which is I bring x downstairs. And you see, that's good because now essentially the numerator and the denominator are both functions of like 1 over x. So when I apply L'Hopital's rule, I'll pick up a derivative of 1 over x both upstairs and downstairs, and those will cancel. And that is where the goodness comes from. Let's see here. I used to be the TA. One of my first jobs in grad school was being the TA for a professor. His name was Chukwu. And I think he was from Nigeria. I think it was Nigeria. I think so. But he had a very, very thick accent. It's hard to understand. He once gave a graph to differential equations, which it was literally nothing more than like a scale, an axis, right? And it had like 5 stars on it. Like there's a star, a star, a star, a star. And then he made like 50 of these and like handed them out. And I have no idea what it meant. I do not know. And the students would come ask me like, what does he want on the extra credit project? And I'd be like, I don't know. See, he had this book about how nations can work together. And like, so nations working together, cooperating, is for the ultimate economic good of all mankind. So some sort of game theory that, you know, if competitors cooperate, they can actually be mutually beneficial, you know, which is actually what the free market's more about. It's about winners and winners, not winners and losers, you know. And but I tell you, all I could tell them was like, I don't know, just do some differential equations, talk about goodness. You like to talk about goodness, is where the goodness is. So whenever I say goodness, it makes me think of that. Anyway, x goes to infinity, so I do L'Hopital's rule, 0 over 0. Sorry, that's a very rare story. I don't tell Chukwu stories much in here. It's a very rare story from me. That's definitely not a rerun. As you get to know professors better, you realize some of their stories are in reruns. Oh, now you know what to do, of course. But I'm gonna double tap this thing, make sure it's dead. Let's see here. So cosine pi over x minus pi over x squared minus 1 over x squared. It actually serves me to. I know I'm doing one of your homework problems. Sorry about that, but you'll get over it. It serves for me to preach at you something else. And if you were atheists, I'd understand you objecting to being preached at. But given where you are and who you possibly are, given that you go to school here, you should like to be preached at. You know? That's one of those sayings I kind of object to, like being preachy. Like, what's wrong with being preachy? Isn't that good? You're trying to affirm a truth to encourage you to become better people. It's a good thing. You should want people to be preachy at you, in some sense. I know it gets a little old sometimes. The other thing is like, oh, that's just academic. Like, if you accept this as a valid saying, why are you here? You know? It's just academic. Yes? Anyway, go ahead. Oh. How? Use ln? Oh, go on. What do you mean by that?
Let's say if you use ln, right? And the ln rule, based off the product rule, would say x plus.
You mean look at the natural log of this thing?
Yeah.
Well, I'd have problems with that because, while x is certainly positive as x goes to infinity, sign oscillates between, well, I suppose. I mean, I guess I don't. I'm trying to decide whether it's. I mean, pi over x looks like what? Right? So as x goes to infinity, I suppose I've got pi over x is approximately, delta, where delta is a small positive quantity, right? Or epsilon, if you like. So sine of epsilon is positive. I guess it still makes sense to take the natural log of this in the limit. But why are we doing this? You take the limit of this?
Yeah.
But why?
Maybe in the context, I'll show you at the class.
Oh, okay.
Sine would be positive.
What's that?
Sine would be positive for all values of x greater than 1. It's between 0 and pi.
Right. I mean, as long as I have sine is 0. Yeah, I mean, sine gets to be 0 again at where? At pi. So I think it's safe. I mean, it's safe to take the ln. I just don't know why we would. There's no need for it, is my point. The place to think about taking natural logs, but I don't do it this way. Some people would say this thing is equal to like y. And then they would say, so if I can show the limit as, n goes to infinity in this case, of the natural log of y is equal to stuff, then y is equal to the exponential of stuff. That's another way to handle those, but I don't do it that way. I mean, you could, but rather than that, we use this exponential of log trick and do it directly, as opposed to calling the limit a name, taking the log of it, solving a corresponding problem, and then exponentiating to get back. That's another way you could do things. Other questions? Yep. 26 and 11.5, a 6? 11.6. Yeah, that is almost identical to what we did there. 26 is 1 plus a over x to the bx. So, I mean, I think it's well, okay, it's different. I know it looks different to you. I'm sorry, it looks the same to me, but that's because, I'm not quite right. Okay, so the point is what you do here, right? I'll just get you started. Is we say, okay, so that's the exponential of the natural log of the limit as n goes to infinity of the 1 plus a over x to the bx, right? But using continuity of the exponential in properties of log, this brings us to the exponential. I already did that, didn't I? Oops. Sorry, I already used I'm sorry. Let me behave. Like I said, I haven't had my coffee. All right, so the limits on all that stuff. So then I use continuity of the exponential and properties of the log to bring the limit as x goes to infinity inside, and then bring the bx down. And then call this thing star and work on it, It's very, very similar to that one. You want to bring the bx. Well, you can leave the b upstairs or downstairs. I leave the b upstairs. Just bring x is equal to 1 over 1 over x, and that'll do it. Yeah.
There's supposed to be a natural log between the bx and the quantity parentheses.
Oh yes, thank you. Goodness gracious, what is wrong with me? Oh, many things, many things. Let's see here. Natural log. There. I feel much better. Thank you. Yeah, the log doesn't just evaporate. Thank you.
Care to explain part B of 11.4, number 41? I think I know what it should be. I don't know why it should be that. I don't know how I can prove it.
Well, I think that's essentially this limit. You're asked to limit as n goes to infinity pn, right? Where pn is what? 2 pi n, is it? 2 pi n you've shown this formula in part A, which is fun trigonometry. So, it's 2Rn sine of pi over n. All right. So I would just say this is the same as 2R sine of pi over n divided by 1 over n. And if I write much more than that, well, extend n continuously, L'Hopital it. Chain rule brings out a pi. Oh yeah, we would like to see 2 pi r, right? It's like, why is there 2 there? Oh, circumference of circle, 2 pi r, yes. So this is, what was this number you're asking about? Number?
41.
Do you guys understand how to derive that? I told the earlier section what they should do is look at, look like a regular polygon, something like this. Oh, that wasn't so regular. Sorry. Well, one person was trying to do it for an irregular polygon, and he was very confused. Understandably so. But the point is, if you just isolate one of these triangles, it has length r here, right? There's this angle. It's pretty easy to see that how many of these are there? For an n-sided regular polygon, there are n of these, right? So the angle in one particular sector is 2 pi over n. And so you just got to figure out, if you've got this triangle, this is length r. You can make a little right triangle here. That's pi over n, right? Because if this is 2 pi over n, that's half of it. And so you just got to figure out, what's this length? Then twice of that gives you the length of one side, but then n times that gives you the net perimeter of a regular polygon. All right, with that, I'm going to hand back the quizzes and talk to you guys about the quizzes in the time that remains. I should have the solution posted to the quiz before too long. You can go ahead and turn the camera off. I already talked about it in the earlier section. There's no sense in recording it.